For this video, I'll be revisiting streams, not the I/O kind, but Java's stream pipelines. When I covered streams previously, I didn't cover parallel streams. That's because I felt it made more sense to include them in this section on asynchronous programming. Parallel streams were introduced in Java 8 along with serial streams. They allow you to perform operations on collections in parallel, thus potentially speeding up data processing. The key advantages of parallel streams are improved performance on multi-core CPUs, simplified code for concurrent processing, automatic workload distribution among available threads. In the last video, you saw ways of using a fork join pool to break up one operation into many smaller ones running in parallel. I did this manually, first by creating a list of callable tasks and then by creating a recursive task that I had the fork join pool invoke. Parallel streams do this work implicitly for us, making them simpler to use. I've created a new project and called it Parallel Streams. I've got the usual main class and main method. I'll start out just like I did in the previous video, getting a random stream of longs as an array. I'll make the length of the array a variable. I'll call it numbers length and set that to 100,000. I'll use the random class to generate a stream of random long values from 1 to 100,000 in this case. I'll call to array on the stream to get an array back. I'll take a snapshot of the UDC time in nanoseconds using the method system.nanotime. I'll execute the average operation, a terminal operation, on a stream of my numbers array. I'll use optionals or else throw method to get that from the optional instance returned. You might remember that this method throws an exception if for some reason the stream doesn't return the average. I'll get the time elapsed, again using system.nanotime, but here I'll subtract the start time from that to get the elapsed time. I'll print out a formatted string that has the average of the array values and the elapsed time in nanoseconds. These values are in the average serial and elapsed serial variables. Running this code, I'll get an average value and the elapsed time in nanoseconds. I'll run it a couple of times, and of course these values will be different each time, but the average should be about half of my number's length value, so about 50,000 right now. I can transform nanoseconds to milliseconds, so I'll do that here, since milliseconds are a bit easier to grasp. I'll add another format specifier and some text for the milliseconds. I'll include the formula to get milliseconds from nanoseconds, which is just dividing by a million. I'll make that million a double, so the result will be a double. Running this, with this change, I can see, when I run it a couple of times, the time is usually somewhere between 5 and 15 milliseconds, though not always, and can be sometimes larger than that. Your elapsed time will be different from mine, depending on what system you're operating on. In the last video, I showed you two ways to perform the summation in parallel parts. The use of the fork join pool with either callable or recursive task is valuable to know, especially if you can divide up your one large unit of work into smaller tasks. In the case of dividing the work over a data set, as we did in that example, using a parallel stream is by far the simplest option. There are two ways to make a stream parallel. The first is simply to include the parallel intermediate operation. I'm going to copy the last four statements I have here and paste a copy directly below. And of course I have errors where I have duplicate variable names. I'll remove the type declaration from the first statement, which is assigning a value to start, since I don't need a separate variable each time for this. I'll change average serial to average parallel on the second statement and elapsed serial to elapsed parallel on the third statement. I have to also change these variables in the system.out.printf statement. I haven't yet made this a parallel stream. It's very easy to turn a stream into a parallel stream. I can add an intermediate operation, parallel, after I get the stream. And that's that. Java will now perform this average operation in parallel using fork join pool's common pool, like I used in the previous video, but it's used implicitly here. I'll run this, and I'll run it several times. Your results may be different, but for my system, the results are interesting and sometimes unexpected. The parallel operation isn't always faster according to my timings here. Let's explore this a little further and execute each of these multiple times and get an average elapsed time difference. I'll start by declaring a couple of variables before I do either of these calculations. I'll create a long variable I'll call delta that'll track the time differences between the serial execution and the parallel execution. I'll set up a variable for the number of times I want to execute these tests and call it iterations. Now, I'll set up a for loop around my two existing tests. I'll loop from 0 to the number of iterations in my variable, so this will execute 100 times to start with. I'll enclose the code in the ending for loop bracket. I'll remove both print statements. I'll include a calculation of the difference between the serial elapsed time and the parallel elapsed time. I'll keep a running total of the differences in the delta field. Next, I'll print out the average delta. I don't really care about the average of the array anymore, since it will generally be half of whatever value I've got in the numbers length field. I'll compare the parallel to the serial, both in nanoseconds and milliseconds. To do that, I'll get the delta divided by the loop iterations for nanoseconds, and for milliseconds, I'll again divide by 1 million. So this code will loop 100 times for the same array and get the average each time using a serial stream, then get the average again next using a parallel stream. It will calculate the difference in elapsed time, subtracting the parallel time from the serial time, which we might assume is higher because you'd expect the serial stream to be slower. We'll print the average difference after the loop. Okay, so I'll run this. For my own test cases, I usually get a negative number, meaning the parallel isn't faster than the serial processing at all. Maybe this surprises you, maybe it doesn't. I'll change the size of my array by changing the value in numbers length from 100,000 and bump that up to 100 million. I'll also change my loop iterations from 100 to 25 because these calculations will take longer. I'll run this again. This time it's going to take longer to run each iteration, so maybe I'll have to wait 10 seconds or so here for this process to complete. When it does complete, I now should see that the parallel processing is faster than the serial. I'll run it a couple of times just to confirm that this remains true over several tests. This is one way to do what's called benchmark testing. Both times I run it, I get a similar result that the parallel stream is somewhere in the neighbourhood of 130 milliseconds faster for this much larger array. I'll run it a third time. So why do you think when my array had 100,000 elements, it wasn't always consistent or it tipped the other way? Why was serial processing faster in the case of a smaller array? Here, you can see the third time finished, and I can again confirm that the parallel processing is doing a better job with my larger array. There's some overhead associated with using parallel streams. Some operations are very fast naturally, like summations and averages. For these types of operations, the overheads involved with parallel streams or operations may actually not be faster as we've seen until your data set gets large enough. Parallel streams introduce some overhead, such as the need to create and manage multiple threads. This overhead can be significant for small arrays. Parallel streams need to synchronize their operations to ensure that the results are correct. This synchronization can also add overhead, especially for small arrays. The cautionary tale here is, don't assume a parallel stream will always improve performance. In fact, there are times that you specify you want to use a parallel stream, Java's optimizations may not even use one. If your collection of data needs to be ordered, this too may affect how well the parallel operations perform. I'll get into these two topics in the next video as we start looking at ordered streams and reductions in parallel, so I'll see you in that next video.